In this video we're going to look at polygons. Polygons are two-dimensional closed shapes composed of straight sides that meet at points called vertices. So this hexagon has 6 vertices and it would have 6 edges, which are the straight line parts. If a polygon's angles and sides are equal, and we make it clear that they're equal by drawing one of these lines through it, and the angles, we can see they've got a double dash through them, so that means that they're all equal. So this is a regular hexagon. If a polygon's angles or sides of length differ, they're called irregular polygons. So this is another hexagon, but because the lengths are all different and the angles are different, then it means it's irregular. Now we should be familiar with the names of many different types of polygons. So a 3-sided polygon is a triangle, a 4 is a quadrilateral, then pentagon, hexagon. Heptagon is the more common term for a 7-sided polygon. Octagon, nonagon and decagon. And a polygon has interior and exterior angles. So if this was our pentagon and it was made up of 5 edges and 5 vertices, if we extend the edges of the polygon out and do that in the same direction, so in this case we're going in an anti-clockwise direction, then what we can see, the angles marked in red are the interior angles, and the angles that we've carried on are the exterior angles. Now in a regular polygon, the exterior angles are all the same, and that's because the interior ones will have to be the same, and because the exterior and interior lie in a straight line, then the exterior must also all be equal. For any polygon, so the interior plus the exterior add up to 180 degrees, and the total of all the exterior angles add up to 360 degrees. And the reason for that is if we start on this line and we turn through the blue angle and then fall along and turn through the blue angle and turn through the blue angle and turn through the blue angle and turn through the blue angle, we've ended up back where we started again. So we've done a number of turns, we've ended up back to the start, which means the number of turns add up to 360. For a regular polygon, the size of each identical exterior angle is found by 360 degrees, so that's the full turn, divided by the number of sides. So 360 divided by n gives you the exterior angle. So with this we could manipulate it that the exterior angle E is 360 over n, or the number of sides would also equal 360 divided by E. And then we have the case where E plus I equals 180. So example 1, find the size of each exterior angle in a regular pentagon, hence find the size of each interior angle. So the exterior angle is 360 divided by n, and in this case, because we've got a pentagon, n equals 5. So E is going to equal 360 divided by 5, which is 72 degrees. To find the interior, we know that I plus E is 180. So I is going to be 180 minus the exterior, which is 72. So the interior angle is 108 degrees. Example 2, find the missing angles. So what we've got then, first of all, if we work with x, what we know is that this is a straight line, so the angles must be 180 degrees. So 110 plus x equals 180, so x then is going to be 70 degrees. Similarly with y, we've got that it's lying in a straight line, so y plus 100 equals 180 degrees. So y then is 80 degrees. And for z, they're lying in a straight line. So z plus 140 equals 180. So z equals 40 degrees. Now to work out w, what we've got is that w is an exterior angle, as is z, as is the 110, and as is this 100. So what we've got then is that 110 plus 100 plus w plus z equals 360 because the exterior angles add up to 360. We know z is 40, so we're going to have w plus 250 equals 360 degrees. So then w is going to equal 110 degrees. Example 3, a regular polygon has an exterior angle of 30. How many sides does it have? So what we know is the exterior angle is 360 divided by n. And if we know that 30 equals 360 divided by n, we could multiply up by n and we get 30n equals 360. And dividing by 30, we get n is 360 over 30, which works out to be 12. So it's 12 sides, so that's a dodecagon. Example 4, a regular polygon has an interior angle of 144. How many sides does it have? So our formula, or any formula that we have for connecting the number of sides and angles, is that the exterior angle is 360 divided by the number of sides. Now we know also that the interior plus the exterior add up to 180 degrees. So if we use this second formula and work out the exterior angle, then we can use that to work out the number of sides. So we've got 144 plus the exterior is 180 degrees. That means the exterior is going to be 36 degrees. So 36 is going to be 360 divided by n. So 30 multiplying up by n, we get 36n is 360. Dividing by 36, we get n equals 10. So it's 10 sides, which is a decagon. Is it possible for a regular polygon to have an interior angle of 101? So we're going to use the same technique as we've done in the last example there, where we know the interior plus exterior is 180. So the exterior is going to be 180 minus 101, which is 79 degrees. So to work out the number of sides it would have, we're going to do the exterior angle is 360 divided by n. So therefore 79 is going to equal 360 over n. Multiplying up by n, we get 79n equals 360. So dividing by 79, we get 4.56. So that's not a whole number, so it's not possible. So we could have an irregular polygon, but we can't have a regular polygon with an interior angle of 101. So to test if a regular polygon can exist with a given exterior angle, we use n equals 360 divided by n. So that's just a manipulation of e equals 360 over n. So e times n equals 360. So n equals 360 over e. We could consider it to be a triangle, like speed, distance, time, or density. So the number of sides is 360 divided by the exterior, or the exterior angle is 360 divided by n. To find the sum of all the interior angles, what we do is we get our polygon and we split it up into triangles. So we can see in this pentagon we've split it into 3 separate triangles, and we know that the angle sum of each triangle, so if we add up all the 3 angles in each triangle, they'll add up to 180. So because we've got 3 triangles in this pentagon, that means that the sum of the angles of the pentagon is going to be 3 times 180, or 540. And this happens for every polygon, where we can always form 2 fewer than the number of sides. So a decagon will have 8 triangles. So the formula then to work out the sum of the interior angles is the number of sides take away 2 times by 180. Now that gives you all of the angles. So to work out what each of the angles are, we divide by the number of sides. So in the case of the decagon, to work out the size of each angle, we do 8 times 360, or 8 times 180. So 10 minus 2 is 8 times 180. And whatever that works out to be, we divide by 10 to get the size of each angle. Example 6, find the sum of the interior angles in a regular 20-sided polygon. So to do that, the sum of the interior angles is n minus 2 times 180. So it's the number of triangles we can form. And that's going to be 20 minus 2 times 180, which is 18 times 180, which is 3,240 degrees. So all 20 angles add up to 3,240. So one interior angle is going to be 3,240 divided by 20, which is 162 degrees. So a regular 20-sided polygon will have 20 angles each of 162 degrees. Example 7, find the value of x. So what we've got first of all is that we can see that there are 1, 2, 3, 4, 5 sides. So we know that the angles inside the pentagon are going to have to add up to n minus 2 times 180, which is 5 minus 2 times 180. So 3 times 180, which is 540 degrees. So that means that 95 plus 115 plus 110 plus 75 plus x must add together to give 540. So we can simplify that to give 395 plus x equals 540. So if we take away 395 from both sides, we get that x equals 145 degrees. So x is 145. Common mistake here would be that you would just find these and add them all together to get 360, but hopefully it would be a giveaway because the 4 angles that we know would add to 360, so we'd know we've done something wrong there. Now, the repeating pattern of polygons that fit together with no gaps is called a tessellation. The total of interior angles around a point must add to 360 degrees exactly. So equilateral triangles will all have angles of 60 degrees and they'll fit together. 6 of them will fit together to form a point. Similarly, squares or rectangles, or in fact any quadrilateral, we could tessellate. All the points will add up to 360. And here we've got hexagons, which is an extension obviously of our equilateral triangle, and the interior angle of a hexagon is 120 degrees, and 3 of those will fit together to give a tessellating pattern.